Have you ever just looked up at a star in the night sky and wondered something? Even with the absolute best telescope, it never looks like a perfect, sharp little point of light, does it? There's always, well, a little bit of a blur. And it turns out, that's not a flaw in our cameras or our telescopes. Nope, it's actually a fundamental mystery that's built right into the fabric of reality itself.
So yeah, why is that? Why can't we get a perfect, infinitely sharp image of anything? The answer, you'll see, isn't just about lenses and optics. To really get it, we've got to take a deep dive into physics, a little bit of math, and, amazingly, the design of our very own eyes.
Okay, look at this. This shows the problem perfectly. On the left, that's what we think we should see, a distant star, a perfect little dot of light, the ideal. But on the right, that's the reality. Any lens, whether it's in a giant telescope or your eyeball, transforms that dot into this blurry pattern, a bright center with these faint rings around it. This unavoidable little blur actually has a name. It's called an Airy disk.
So what gives? Is it just, a smudge on the lens? Some kind of defect? Not even close. This blur is an absolute, unavoidable consequence of how light itself works. We've basically hit one of the fundamental limits of seeing.
And to get to the bottom of this whole thing, we have to wrap our heads around one core idea. Light doesn't just travel in a straight line like some tiny particle. It also behaves like a wave, with crests and troughs, just like a ripple spreading out in a pond. And that wavy nature of light, that is the key to solving this whole mystery.
So, how in the world do we analyze something as complex as a light wave? Well, we're going to need a pretty special tool for the job. Let's talk about decoding waves using this brilliant mathematical idea called the Fourier transform. Seriously, think of it like a universal recipe decoder for any kind of wave you can imagine. To put it simply, the Fourier transform can take any complex signal, I'm talking about the sound of a guitar chord or, say, the shape of a light wave, and it tells you exactly which simple smooth sine waves you need to add together to build it. It gives you the entire recipe, the ingredients, how much of each to use, the whole shebang.
All right, let's see this in action. We start with some super simple ingredients, right? Like these two basic sine waves.
Now when we add them up, boom, we get this more complex black waveform. See that dashed line? That's our target. And you can see we're already starting to get closer to matching it.
And really, the process is that simple. You just keep adding the right ingredient waves into the mix. And with every new wave you add, your final shape gets a little more complex, a little more precise.
So let's get a little fancier. Let's expand our recipe with 4 different ingredient waves. And when we add all of those up, what do we get? The result is a nearly perfect match for our target shape. Now here's the key takeaway from all of this. With enough simple sine waves, you can build any shape you can possibly imagine.
And this is the real power of the Fourier transform. It can take that complex wave we built on the left, and it gives us its simple, clean recipe on the right, a fingerprint showing the exact ingredients and how much of each went into the mix.
Okay, so that's a super cool math tool, right? But what on earth does a recipe decoder have to do with blurry stars? Well, this is where it gets really interesting. Let's apply this whole idea to light itself and uncover that blurry fingerprint.
So here's the piece of physics that connects everything together. Whenever light waves pass through any kind of opening, what scientists call an aperture, they don't just keep going in a perfectly straight line. They actually spread out. They sort of bend around the edges. This behavior is called diffraction. And it doesn't just happen with light, it happens with all waves.
And now, prepare for the aha moment. On the left, you see a simple circular hole, just like the pupil of your eye. When light passes through it, it creates that specific diffraction pattern on the right. And here is the mind-blowing part. That pattern is the 2D Fourier transform of the circle. It's the exact same Airy disk we saw at the very beginning. Physics itself is literally calculating the Fourier recipe for us.
I mean, let's just let that sink in. The physical act of light passing through the pupil of your eye is a Fourier transform. Nature is doing the math, turning what should be a perfect point of light into that iconic blurry pattern. This unavoidable blur actually has an official name. It's called the point spread function, or PSF for short. And you should really think of it as the unique blurry fingerprint of any optical system. Every single point of light that enters your eye gets smeared out or spread into this exact shape. It's not a flaw, it's a feature of physics. So, physics hands us this unavoidable blur. But that's really only half the story.
The other half is all about how our own biology has evolved to deal with this fundamental limit. This is where the physics of optics smacks right into the anatomy of the human eye.
See, the resolution of our vision, how much detail we can see, is basically a competition between two things. First, you've got the optical limit on the left. That's the physical size of that blurry PSF. Then on the right, you have the anatomical limit, which is just the spacing of our photoreceptor cells, the pixels in our retina. You can't see details smaller than your pixels, but you also can't see details that physics has already blurred out for you.
So how close can two of these blurry spots get before our brain just sees them as one big blob? Well, scientists have a rule for this called the Rayleigh Criterion, and it basically says that you can just tell 2 points apart when the bright center of one blurry spot falls directly on top of the first dark ring of the other one. Any closer, and they just merge together.
And here's what that looks like in action. Look at position 1. The 2 points are clearly separate, no problem. Now look at position 2. They've just hit that Rayleigh criterion limit. You can barely make out that there are 2 peaks there. But by the time they get to position 3, forget it. They've completely merged into a single unresolved blob. This is the absolute limit of what any lens can resolve.
Okay, so we've got a blur limit from the laws of physics, and we've got a pixel limit from our own biology. So the ultimate question is, how well do they match up? Well, the answer is, it's nothing short of astonishing.
And here it is. This is the punchline. The optical limit, the one dictated by physics, means the smallest possible blur our eye can form is about 49.8 arcseconds wide. Meanwhile, the anatomical limit, based on how closely packed the cone cells are in our retina, allows us to resolve details down to about 49.2 arcseconds. Just look at those numbers. They're nearly identical. Evolution has given our eyes pixels that are perfectly sized to capture the image physics provides, no more and no less. You know, we started this whole thing by asking why our vision is imperfect. But maybe that was the wrong question all along. What if that blur isn't a flaw at all? What if it's a sign of perfect adaptation? What if the human eye is this incredible masterpiece of biological engineering, not fighting against the laws of physics, but designed to be as good as the universe will possibly allow? It seems our vision isn't flawed after all, it's flawlessly adapted.